Good afternoon, everyone. My name is Valerio Orlandini. I am a doctoral student at the Conservatory of Florence, Italy, and also a musician. And today I'm going to talk to you about a project that I'm following from about 1 year, 1 year and a half, centered about sound descriptors and how can be used in different fields of audio, from artistic purposes to more scientific ones. Before diving into my project, let's see what are sound descriptors or audio descriptors, which are basically the same. They are numerical representations of the characteristics of a signal. That goes beyond the simple observation of the amplitude or how the spectrum is organized. There are sort of metadata for sound, and their definition began in the 90s and had a sort of standardization with the MPEG-7 standard, and also some papers that was out around year 2000. But still today, there is not a universal terminology. So you can find, for example, the same sound descriptor calculated in two different ways, or with even different meaning. Where are sound descriptors used? They're used in different contexts. For example, in music information retrieval, in musicology, in data analysis, for concatenated synthesis, for real-time audio interactions, and some of these examples will be investigated later when I will talk about my project. So we said that there is not a common definition of sound descriptors. What you see here is not the definitive list, but simply those implemented currently in my software. But even those, as I said, can be calculated in different ways. As you can see, some of them are calculated in the time domain, and most of them actually, in the frequency domain. Some are well known, like the root mean square or the peak of the signal. Others have more exoteric or exotic names. But the purpose of all these sound descriptors is actually to describe a sound with in a finer grained way instead of simply looking at the waveform. Sometimes there is a distinction between low, mid, and high level the sound descriptor according to how abstract they are. Sometimes high level descriptors are like those which express a sentiment towards music, like how happy or sad it is, so on. While low and mid-level descriptors are those that you would can actually calculate in a certain way directly from the information about the raw samples in the amplitude, or the magnitudes calculated with a fast Fourier transform. So why we use sound descriptors? I already said that, but to enter more in depth, you can move beyond from one side to the typical calculation and sound descriptions only based on amplitude on raw spectrogram. But from the other one, you can move beyond subjective descriptors like this sounds warm. Using some terminology that can be shared between artists, also researchers. Moreover, you can use those to analyze in-depth sounds, for example, in musicology, to identify different sections inside a track, or to find similarities between tracks, or in audiovisual arts, and we will see some example in a few minutes. So now that we barely know what a sound descriptor is. Why I'm talking about this? Because I developed this project that is called The Informer, which is a comprehensive open source solution for real-time feature extractions and broadcasting of sound descriptors. It began simply as a plugin plugin and standalone application written with Juice, so multi-format and multi-platform. I was using this just to for some audiovisual experiments for my audiovisual installations when I play live and so on. Then, since I saw that it worked rather well, I decided to add some other parts to the project, like a VCV Rack module and a library, both in C++ and Python, so that you can use the algorithms that I implemented in the plugin version also in your third-party software. Moreover, you can find the package that it's all on GitHub, a Max for Live device that receives this data from the plugin so that you can use this data inside Ableton Live. Here you can see the screenshots of the plugin version and of the VCV Rack version. The plugin basically calculates in real time sound descriptors, and then it broadcasts them through Open Sound Control Protocol. Moreover, the VCV Rack module also outputs the calculations directly with single output so that you can use them as a source of modulation for other rack modules. So basically, the workflow is this. The descriptors is carried on starting from the audio buffer and the FFT. And then these descriptors are delivered through Open Sound Control in the plugin version, while the libraries returns the values so that you can use in your third-party software. So you can use it both for artistic purposes, and it is addressed for example, for the musician who doesn't know how to calculate and how to use these descriptors in a more scientific environment, but also towards developers who wants to use it in their software. Of course, it's not the first library ever that calculates descriptor, but I will show you later some particular features that maybe can be of your interest, at least for you developers here. So let's see it in action instead of keep on talking of what it can do. The first example is an audio-video interaction. So basically, it is the reason why I started this project, actually. So I want to transform the information about my sounds into something visual. Not only using the lower bands, higher bands of sounds, or how loud it is and so on, but trying to link more specific properties. For example, the centroid of a sound, which is the point of balance of a spectrum, can be represented in some more particular way instead of just stretching a figure based on how many bass the sound has, and so on. So this is an example of a simple track of mine that was analyzed in real time through the Informer plugin, and then the Open Sound Control messages were sent to Touch Designer, and in Touch Designer I used to modify the parameters of a simple 3D shape. Of course, we want to watch the video in its entirety. I will jump here and there just to give you an example. Okay, just to give you an idea. Of course, the relationship between sound descriptors, and shapes are not immediately visible. Of course, it's also an artistic choice, but as you can see, just analyzing already mixed track, you can find something more particular than just what you do with the bands or the amplitude. But there is not only audio to video interaction, but you can use it also for audio to audio interaction. For example, using the Max for Live receiver device, or with the VCV Rack module, or of course using any open sound control capable software like Max MSP, Pure Data, and so on. Imagine, for example, to drive the cutoff of a filter according to the spectral centroid of another sound, so that the two sounds don't clash, or to adjust the amount of a reverb according to the spectral spread, so how many frequencies are spread in the spectrum, so that the result is not too dense. Or you can drive the noise amount of an oscillator according to the entropy of another sound, so the texture remains noisy but not that much, for example. And with the Max for Live device, this is immediate, but you can use it in any kind of software, of course. Then we go to the more nerdy part of this presentation, because from the algorithms I wrote for the plugin, I implemented a library, initially for C++, and its features are that it is an header-only library, that it depends only on C++ standard library, so no other dependencies needed, and it has two different interfaces. One is a function-based interface. So there are single functions, you pass the necessary data, and the function centroid gives you the centroid of that sound. The other one, which is, you can see an example here, is a class-based interface that is easier probably to use, because you don't have to reload the data for each descriptor, but you can store them and then make the calculations all at once. This is a complete example of how you can use the library. No other lines of code needed. You include the header, you instantiate a class, then you set the buffer, so putting the audio data. You set the magnitudes of the FFT. If you have the result of real valued FFT without already the magnitudes ready, for example, Juice can do this, but other FFT library that doesn't have a function like this, there is a utility function set STFT, and then the library computes for you the magnitudes in the format it is expecting. Then you call the function compute descriptors, and you want a centroid, just call the function get frequency descriptor centroid, and you have your centroid. The Python version is the same. There are simply bindings made with PyBind 11. Also the Python library has the two different interfaces, the single functions and the class-based ones, and it is thought to be directly compatible with the many other Python libraries used in scientific research, in analysis, in deep learning, and so on. So you can directly pass NumPy arrays, and what you have in return, you can pass directly, for example, to matplotlib, as in this picture, without any kind of data conversion. You see this example, it was made with Librosa, that loaded a sound file and performed the fast Fourier transform. Then the informal library calculated the various descriptors, and then everything is plotted to this graph. Just some final stuff before the presentation is over. The licenses of the library are GPL version 3 for the plugin and the VCV Rack module and for the standalone version, while the library is MIT licensed, so you can use it in your closed source software without issues. Everything is on GitHub. You can scan this QR code to go directly to the repository. You will find in the repository also the binary compiled versions from Mac OS, Windows, and Linux of the plugins, the VCV Rack module, and the Max for Live device. And if you have any questions, you can find me here on Discord, everywhere. And thank you for your attention.